Your simple water is a lie. Water looks boring because you've seen it your whole life. That's the trick. Familiar things are the easiest places to hide, the strangest physics. You were taught that matter behaves politely. Cool it down and it shrinks. Freeze it and it gets denser. Make it solid and it sinks. That's what most substances do. Water doesn't. Water expands when it freezes. Its solid form floats. It reaches maximum density at 4 degrees Celsius and then starts doing the opposite of what should happen. It forms an elastic skin you can't see, strong enough to hold insects. It climbs up thin tubes like it's disobeying gravity. It stores heat like a battery and releases it slowly, controlling storms, oceans, and climate. And it dissolves more different chemicals than almost any liquid, which is one reason life can exist at all. So what's the disturbing part? It's not that water breaks physics. It's that water exposes how shallow your mental picture of physics is. Water is a liquid that behaves like a living network, constantly forming and breaking microscopic connections, so your common sense rules don't apply. Let's take it apart carefully. The rule water breaks, density and freezing. Let's begin with the rule you trust without even knowing you trust it. Cooling makes things contract. Atoms jiggle less, settle closer together, take up less space. That's why metal bridges need expansion joints. That's why warm air rises. That's why a hot balloon is larger than a cold one. It's not a law in a deep sense, but it's so widespread that your brain treats it as universal. Now apply it to freezing. Freezing is supposed to be the ultimate packing process. Molecules stop sliding around, lock into a solid, and typically pack more tightly than they did in liquid form. That's why most solids sink in their own liquids. Solid iron sinks in molten iron. Solid wax sinks in melted wax. Solid carbon dioxide doesn't even have a liquid at normal pressure, but the pattern holds generally. Solid is denser. Water does the opposite. When water freezes into ordinary ice, it expands by about 9%. That means the solid occupies more volume than the liquid for the same mass. That means ice is less dense, so it floats. This is not a cute exception. It's a blatant betrayal of the naive picture of matter. And it's not just the freezing point. Water does something even more insulting. As you cool liquid water from room temperature, it gets denser as expected until it reaches about 4 degrees Celsius. At that point, it reaches its maximum density. Then as it cools further towards 0 degrees Celsius, it starts expanding again. So water breaks the rule twice. It expands. As it approaches freezing, it expands when it freezes. If you want to understand why, you must stop thinking of water molecules as little billiard balls. They are not billiard balls. They are tiny electrical machines with a very particular geometry. Hydrogen bonds, the hidden network. Water is H2O, yes, but H2O is not the explanation, it's the label on the box. The oxygen atom attracts electrons more strongly than hydrogen does. That makes the oxygen end of the molecule slightly negative and the hydrogen end slightly positive. The molecule is polar. It has a built-in electrical asymmetry. So when two water molecules come near each other, something happens that's weak individually but powerful collectively. The positive hydrogen on one molecule is attracted to the negative oxygen on another. That attraction is called the hydrogen bond. Now, a hydrogen bond is not a full chemical bond, like the one holding the H to the O inside a molecule. It's weaker, it breaks easily. At room temperature, hydrogen bonds are breaking and reforming constantly on timescales of trillionths of a second. But here's the crucial point. Each water molecule can form up to 4 hydrogen bonds in a roughly tetrahedral arrangement. That means water is constantly trying to form a network. Not a permanent crystal network, unless it freezes, but a shifting, reorganizing network. This is the disturbing idea. Liquid water isn't molecules floating around. It's a society of molecules, continuously forming temporary partnerships. Think of a crowded dance floor. People are holding hands in groups, then letting go, then forming new groups over and over. You can't describe the crowd by tracking one person alone. The crowd's behavior is a collective phenomena. Water's properties are collective phenomena. Once you accept that, the rule breaking becomes less mysterious. It's not that the molecules ignore physics, it's that the network changes the effective structure of the liquid. Why ice floats, and why that saves life. When water freezes, the dance floor becomes choreography. The hydrogen bonds stop rearranging randomly and lock into an ordered crystal lattice. The most common form of ice on Earth Ice E forms a hexagonal structure. It's beautiful and it's also extremely important. Hydrogen bonds prefer a geometry that isn't the tightest packing. They prefer angles that create an open framework. In ice, each molecule sits in a structure that maximizes stable hydrogen bonding, even if that creates empty space. That empty space is not a flaw, it's the consequence of the bonding geometry. And empty space means lower density. So the reason ice floats is not water is special in some mystical sense. It's watermolecules form hydrogen bonds. Hydrogen bonds enforce a particular geometry. That geometry creates an open lattice. Open lattice means lower density. Lower density means floating ice. Now let's talk about why that matters. Because it's not just trivia. If ice were denser than water, ice would sink. Lakes would freeze from the bottom up. The first ice would form at the surface, sink, then more would form and sink again, building layers of ice on the bottom. Each winter, lakes would accumulate more bottom ice. Eventually, many lakes would become solid permanently. That would devastate freshwater ecosystems. Fish and aquatic life rely on liquid water beneath a surface ice layer. The floating ice actually insulates the water below and allows life to survive winter. If ice sank, the planet's heat transport and ocean circulation would be different. Climate would behave differently. The stability of surface environments could be compromised. Life might still exist in some form, but the particular kind of complex biosphere we know would be far less likely. So water's rule breaking is not a party trick. It's a global engineering feature of nature. And here comes the uncomfortable part. We like to think physics is a list of simple rules and everything follows them in neat lines. Water is proof that even when the underlying laws are simple electromagnetism and quantum mechanics, the collective behavior becomes surprising. The rules were never broken. Your shortcut model was the 4 degrees Celsius, mystery, water's density, reversal. Now we reach one of the most puzzling behaviors of water. And if you're not slightly disturbed by it, you probably haven't thought about it carefully enough. You would expect a liquid to behave in a simple way when cooled. Lower temperature means molecules move less. Less motion means molecules settle closer together. Closer packing means higher density. That works perfectly for most liquids. Water starts out obeying the rule. Cool liquid water from 30 degrees Celsius to 20 degrees Celsius, it becomes denser. Cool at 2 degrees C, denser still. Everything looks normal. Then something strange happens. At 4 degrees Celsius, water reaches its maximum density. That is the point where the molecules are packed together as tightly as they are ever going to be in liquid form. But if you keep cooling the water from 4 degrees Celsius down towards 0 degrees Celsius, the density stops increasing. It reverses. The water begins expanding again. This means cold water near freezing is actually less dense than water at 4 degrees Celsius. If you are used to thinking about matter in simple mechanical terms, this should feel almost illegal. How could molecules moving less occupy more space? The answer, once again, is the hydrogen bond network. The tug of war inside liquid water. In liquid water, there are two competing effects happening simultaneously. The first effect is the one you expect. When temperature drops, molecular motion slows. Slower molecules collide less violently and can settle closer together. This tends to increase density. But the second effect is more subtle. As temperature decreases, hydrogen bonds become more stable. Molecules spend more time connected in tetrahedral arrangements, the same kind of structure that will eventually dominate in ice. That tetrahedral network contains open spaces. In other words, the more organized the hydrogen bond network becomes, the more empty volume appears between molecules. So there is a competition. Cooling tries to compress the liquid. Hydrogen bonding tries to open it up. At temperatures above 4 degrees Celsius, the compression effect wins. Below 4 degrees Celsius, the network building effect wins. And at exactly 4 degrees Celsius, the two effects balance. That balance point is why lakes behave the way they do in winter. Why lakes freeze from the top. Imagine a lake in autumn as the temperature begins to drop. Surface water cools first. As it cools down toward 4 degrees Celsius, it becomes denser and sinks. Warmer water rises to replace it. The lake mixes. Eventually, the entire lake reaches roughly 4 degrees Celsius. Then winter keeps cooling the surface. But now something new happens. Water at the surface cools below 4 degrees Celsius, becoming less dense than the water below it. Instead of sinking, it stays on top. The colder water accumulates at the surface. When it reaches 0 degrees Celsius, it freezes. Ice forms only at the top. Underneath that ice layer sits water still close to 4 degrees Celsius, dense, stable, and liquid. Fish survive. Plants survive. The lake becomes a protected system. Without the 4 degrees Celsius density anomaly, lakes would freeze solid from the bottom upward. Many freshwater ecosystems would not exist. A single molecular geometry, the tetrahedral hydrogen bond structure, determines the survival of entire planetary ecosystem. That should give you pause. Physics at the scale of electrons decides the fate of forests and fish. Surface tension, water's invisible skin. Now let's examine another property that makes water look almost magical: surface tension. If you've ever watched a water droplet sitting on a leaf, you may have noticed that it forms a nearly perfect sphere. Liquids try to minimize their surface area. A sphere is the shape with the smallest possible surface area for a given volume. But water's surface tension is unusually strong. Strong enough for insects like water striders to walk across ponds. Strong enough that a carefully placed paperclip can float. Strong enough to create droplets that resist breaking apart. Why? Again, hydrogen bonding. Inside the liquid, each molecule is surrounded by neighbors in all directions. The forces cancel out. But at the surface, molecules have neighbors only below them and beside them. They are missing neighbors above. That means the hydrogen bonds pull the surface molecules inward. The surface behaves like a stretched membrane. This membrane is not a separate layer. It's simply the result of molecular forces acting unevenly at the boundary. But the result is dramatic. The surface of water behaves almost like an elastic skin. That skin is constantly forming and reforming as molecules move. But on average, it behaves as if the surface were under tension. And water's tension is far stronger than most liquids of similar molecular size. The strength of water's surface, to give you a sense of scale, water's surface tension at room temperature is about 72 millinewtons per meter. That's far higher than alcohol, gasoline, or most organic liquids. Why? Because hydrogen bonds are directional and cooperative. When many water molecules interact simultaneously, the network amplifies their collective attraction. This makes the surface energetically expensive to break, which is why droplets bead up, which is why raindrops form spheres as they fall, which is why insects can skate across ponds, and which is why bubbles require soap. Soap molecules interfere with hydrogen bonding at the surface. They weaken the network. That lowers surface tension, allowing bubbles to stretch thin films without snapping. Soap doesn't clean by magic. It manipulates molecular forces. When physics looks like magic, this is something Richard Feynman loved pointing out. Nature is under no obligation to be simple at the level of human intuition. The rules themselves are simple. Electromagnetism and quantum mechanics govern molecular interactions. But when billions of molecules interact collectively, the emergent behavior can look strange. Water climbs glass tubes. Water beads into droplets. Water resists being pulled apart. None of this violates physics. It simply means that the physics is deeper than the cartoon model in your head. And the deeper you go, the more fascinating it becomes. Because surface tension is not just a curiosity. It enables entire biological systems. Biology built on surface tension. Tiny organisms rely on surface tension to remain at the water's surface. Plant leaves rely on it to hold droplets. Soil moisture relies on it to maintain thin water films around particles. Even the structure of lungs involves surface tension, which is why the body produces surfactants to control it. The physics of hydrogen bonding reaches from microscopic molecular interactions all the way to the architecture of life. And we still have several strange behaviors left to explain, because water hasn't finished surprising us yet. Capillary action. Water climbs without help. Now we come to something that looks so strange that for centuries people thought it was a kind of hidden life force. Water climbs, not metaphorically, literally. Put a narrow glass tube into a cup of water, and the water level inside the tube will rise above the surrounding surface. No pump, no pressure difference you can see. Gravity pulling downward, and yet the water moves upward. This phenomenon is called capillary action, and if you've ever dipped a paper towel into a puddle and watched the water crawl upward through the fibers, you've already seen it happen. Plants rely on it. Soil relies on it. Your own body relies on it. But the physics behind it is deceptively simple. Two forces are competing again. Cohesion, the attraction between water molecules due to hydrogen bonding. Adhesion, the attraction between water molecules and the surface of another material, such as glass or plant fibers. If adhesion to the surface is stronger than cohesion between water molecules, the water will climb the walls of the container. But because water molecules are strongly bonded to each other through hydrogen bonding, when one molecule climbs, it pulls its neighbors with it. The result is a rising column of liquid. The smaller the tube, the higher the climb. That is why water rises higher in narrow plant vessels than in wider pipes. How trees use this physics trick. A tall tree can lift water more than 100 meters from roots to leaves. Think about that. No mechanical pump, no beating heart pushing the fluid, just molecular forces, sunlight, and evaporation. Here's roughly how it works. Water evaporates from the tiny pores in leaves. This process is called transpiration. When a water molecule escapes into the air, it pulls on the column of molecules behind it through hydrogen bonding. That tension propagates downward through the plant's vascular system. Because the water molecules stick to the walls of the plant's xylem vessels, adhesion, and to each other, cohesion, the column remains intact. So evaporation at the top literally pulls water upward from the soil. You could describe it poetically. The sun pulls water out of the ground through trees. But the actual mechanism is a network of hydrogen bonds transmitting microscopic tension across millions of molecules. Once again, water's strange collective behavior allows something extraordinary. Forests exist partly because hydrogen bonds exist. Heat capacity. Water controls the planet. Now let's talk about something even more powerful than water climbing trees. Water controls the temperature of the planet. This happens because water has an unusually high heat capacity. Heat capacity is the amount of energy required to change a substance's temperature. If a material has low heat capacity, it warms quickly and cools quickly. If it has high heat capacity, it absorbs large amounts of heat before its temperature changes. Water's heat capacity is enormous compared with most liquids. This means water can absorb a huge amount of thermal energy without changing temperature very much. That property stabilizes climates. Why oceans control climate? Think about a coastal city. During the day, land heats up quickly. At night, land cools quickly. But the ocean changes temperature very slowly. During the day, the ocean absorbs heat without becoming dramatically warmer. At night, it releases heat slowly. The ocean acts like a thermal battery. Without this buffering effect, daily temperature swings would be far more extreme. Deserts illustrate what happens when water is absent. Dry desert environments heat rapidly during the day and lose heat rapidly at night. Temperatures may swing by 30 degrees Celsius or more within hours. Near oceans, the swings are much smaller. Water moderates the climate. This is not a small effect. The oceans store about 90% of the excess heat trapped by greenhouse gases in Earth's atmosphere. Water is the planet's primary temperature regulator. The molecular reason, why does water have such a high heat capacity? Again, hydrogen bonding. When you heat water, energy doesn't just increase molecular motion. A large portion of the energy goes into breaking hydrogen bonds. Breaking those bonds requires energy. But when the bonds break, temperature doesn't immediately rise. Energy is absorbed without a large change in molecular speed. This means water can absorb huge amounts of heat before getting hot. And when water cools, hydrogen bonds reform, releasing energy gradually. So water stores and releases thermal energy like a slow-moving reservoir. Without this property, Earth's climate would be chaotic. Storm systems would behave different. Ocean circulation would weaken. Many ecosystems would struggle to survive. All because a molecule prefers to share electrons unevenly. The disturbing answer, your intuition is wrong. Now we reach the disturbing conclusion promised in the title. Water does not break the rules of physics. Your intuition about physics is incomplete. The laws themselves are simple. Electromagnetism describes how charged particles interact. Quantum mechanics describes how electrons occupy orbitals and form bonds. These two theories determine the behavior of atoms and molecules. Nothing about water violates those laws. What surprises us is emergence. When millions or billions of particles interact, new patterns appear. Patterns that are not obvious from the rules governing individual particles. Think about traffic. Each car obeys simple rules. Accelerate, brake, follow lanes. But large numbers of cars interacting produce traffic jams, wave patterns, and gridlocks. The behavior of the system is more complex than the behavior of any individual component. Water is like that. One molecule is simple. Billions of molecules interacting through hydrogen bonds create a dynamic network. That network produces anomalies. Ice floats. Water expands near freezing. Surface tension becomes enormous. Water climbs plants. Water stabilizes climate. None of these violate physics. They simply demonstrate that collective behavior can surprise you. Richard Feynman once emphasized something very important about science. Nature does not care about your common sense. Your common sense evolved to help you throw rocks, catch food, and avoid predators. It was never designed to understand molecular networks or quantum forces. So when water behaves strangely, the correct reaction is not disbelief. The correct reaction is curiosity. Why does the network behave this way? How do microscopic interactions produce macroscopic effects? Physics is not about memorizing rules. It is about understanding the deeper structures behind those rules. And water is one of the most beautiful examples we have, because the more carefully you examine it, the less ordinary it becomes. Water as the universal solvent. Now we come to another strange property of water. Water dissolves more substances than almost any other liquid on Earth. Because of this, scientists often call it the universal solvent. But that phrase can be misleading. Water doesn't dissolve everything. Oils, fats, and many organic molecules resist dissolving in it. Yet compared with most liquids, water can break apart and surround an astonishing variety of materials. Salt disappears in water, sugar disappears, minerals dissolve, even gases such as oxygen and carbon dioxide dissolve into it. Why? Once again, the answer comes back to something we already encountered, the polarity of the water molecule. Remember, the oxygen atom carries a slight negative charge, and the hydrogen atoms carry slight positive charges. This uneven charge distribution allows water molecules to interact strongly with other charged particles. When salt dissolves in water, something remarkable happens. Salt crystals are made of sodium ions and chloride ions locked into a rigid lattice. When the crystal enters water, the water molecules orient themselves around the ions. The negatively charged oxygen side of the water molecules surrounds sodium ions. The positively charged hydrogen sides surround chloride ions. The water molecules essentially pull the ions apart, stabilizing them individually. Instead of remaining stuck together in a crystal, the ions disperse throughout the liquid. The solid dissolves. But here's the interesting part. The ions are not just floating randomly in water. They are surrounded by hydration shells, layers of water molecules oriented in specific directions due to electric attraction. So dissolution is not simply mixing, it is molecular reorganization. Water reshapes its hydrogen bond network to accommodate foreign particles. Why this matters for life? This dissolving power is the reason life is possible. Inside every living cell is a watery environment filled with dissolved molecules, salts, proteins, sugars, nucleic acids. Biochemical reactions require molecules to move freely and collide. Without a solvent to carry them, these reactions would be nearly impossible. Water creates a fluid medium where molecules can diffuse, interact, and rearrange. Think of a cell as a bustling city. Proteins are machines. DNA stores instructions. Ions carry signals. But none of these components could move effectively without water acting as the transportation system. Life does not just contain water. Life depends on water's ability to dissolve and transport molecules. And once again, that ability emerges from something extremely simple, the polarity of the water molecule, water's strange expansion power. Another consequence of water's unusual behavior is its enormous mechanical force when freezing. You may have seen this happen without realizing the physics behind it. A glass bottle filled with water bursts when frozen. Rocks crack during winter in mountainous regions. Road surfaces break apart after repeated freeze-thaw cycles. All of these phenomena originate from the same microscopic cause. Water expands when it freezes. When liquid water becomes ice, the hydrogen bond network locks into that open hexagonal lattice we discussed earlier. This structure occupies about 9% more volume than the liquid state. 9% might sound small, but when confined in a rigid space, that expansion produces enormous pressure. The pressure generated during freezing can exceed 200 megapascals, more than enough to fracture stone. This process is known as frost weathering. Water seeps into tiny cracks in rocks. When temperatures drop, the water freezes and expands, forcing the cracks wider. Over many cycles, entire rocks split apart. Mountains are slowly carved by this process. Glaciers grind rock into powder. Even soil formation partly depends on freezing water expanding inside rock fractures. So water doesn't just shape biology, it shapes geology. Once again, molecular behavior scales upward to planetary effects. The quantum roots of water's behavior. At this point, you might wonder something deeper. Why does the water molecule have this strange polarity in the first place? Why does oxygen attract electrons more strongly than hydrogen? Why do hydrogen bonds form at all? The answer lies in quantum mechanics. Electrons do not orbit atoms like planets around a star. Instead, they occupy probability clouds known as orbitals. These orbitals determine how atoms interact when they form molecules. Oxygen has 8 electrons. Hydrogen has 1. When oxygen bonds with 2 hydrogen atoms, the electrons are shared, but not evenly. Oxygen's stronger electric pull shifts the electron cloud slightly toward itself. This imbalance creates the dipole moment of the water molecule, and that dipole moment allows hydrogen bonds to form. Hydrogen bonds, in turn, create the entire network structure responsible for water's unusual properties. So the behavior of oceans, rivers, clouds, and life itself ultimately traces back to the shape of electron orbitals. Quantum mechanics determines the arrangement of electrons. Electron arrangements determine molecular geometry. Molecular geometry determines hydrogen bonding. Hydrogen bonding determines the strange macroscopic properties of water. This chain of causes stretches from the quantum world all the way to planetary systems, which is exactly the kind of layered explanation that fascinated physicists like Richard Feynman. He often pointed out that nature's complexity arises from simple laws applied repeatedly. The beauty lies in how those simple laws combine. If you take one message from this story, it should be this: physics rarely becomes simpler when you look closer. It becomes richer. Water seems ordinary because we interact with it every day. But when examined scientifically, it becomes one of the most complex and fascinating substances in the universe. The same molecule that forms raindrops also stabilizes climates, enables life, fractures mountains, and regulates planetary temperature, all because of a tiny imbalance in electric charge between oxygen and hydrogen. That is the power of physics. Small rules, huge consequences. Supercooled water, liquid below freezing. Up to this point, water has already violated enough expectations to make us uncomfortable. But nature isn't finished surprising us. Water can remain liquid below its normal freezing temperature. This phenomenon is called supercooling. Under ordinary conditions, water freezes at 0 degrees Celsius. But if the water is extremely pure and undisturbed, it can remain liquid even when cooled several degrees below freezing. Scientists have observed water staying liquid at 10 degrees Celsius, 20 degrees Celsius, and sometimes even colder. At those temperatures, the molecules are moving slowly enough that freezing should occur, yet the water remains liquid. Why? Because freezing requires more than just low temperature. It requires nucleation, a tiny starting point where ice crystals can begin forming. In everyday water, impurities like dust particles provide these nucleation points. Ice crystals begin forming around them, but in extremely clean water, there may be no suitable surface for the ice lattice to begin. The molecules may want to arrange themselves into ice, but they lack a starting template. So the liquid state persists. The water becomes metastable, balanced between liquid and solid. And here is where things become dramatic. If supercooled water is disturbed even slightly, it can freeze instantly. A small vibration, a sudden movement, or the introduction of a tiny particle can trigger the formation of the ice lattice. Within milliseconds, the entire volume crystallizes. You can actually see the freezing wave propagate through the liquid. It looks like time-lapse ice formation happening in real time. This sudden transformation illustrates something profound about physics. The state of matter is not determined only by temperature. It is determined by energy barriers and microscopic structure. Nature sometimes waits for the right trigger before changing states. Supercooled water in the atmosphere. This strange property plays an enormous role in weather. High in the atmosphere, clouds often contain droplets of supercooled water. These droplets can remain liquid at temperatures far below freezing. When an ice crystal forms inside the cloud, the surrounding droplets rapidly freeze onto it. The crystal grows. Eventually, it becomes heavy enough to fall. Snowflakes are born. So the delicate geometry of snow crystals ultimately depends on the physics of supercooled water. Even airplane wings are affected. Aircraft flying through cold clouds can encounter supercooled droplets that freeze instantly upon contact with the wing surface. Ice accumulation can become dangerous, which is why aircraft often carry de-icing systems. Once again, water's microscopic behavior reaches upward into atmospheric physics and global weather systems. Water's role in climate and oceans. We previously discussed water's high heat capacity, but that is only part of its influence on climate. The oceans act as enormous reservoirs of energy. Because water stores heat efficiently, it absorbs solar energy during warm periods and releases it slowly during cooler periods. This stabilizes global temperatures. But oceans do more than store heat. They also transport heat across the planet. Ocean currents move warm water from equatorial regions toward the poles. One of the most famous examples is the Gulf Stream. Warm water from the Gulf of Mexico travels across the Atlantic toward Europe. This current keeps Western Europe far warmer than regions at similar latitudes elsewhere in the world. Without ocean circulation, climate patterns would change dramatically. Many regions would become colder. Weather systems would shift. Agriculture and ecosystems would be affected worldwide. Once again, the entire system relies on the unusual physical properties of water. If water had a lower heat capacity or behaved like most liquids, the oceans would not moderate global temperatures so effectively. Our planet would be far less stable. The water cycle. Water also moves continuously through Earth's environment. Evaporation lifts water into the atmosphere. Condensation forms clouds. Precipitation returns water to land and oceans. This cycle redistributes heat across the planet. When water evaporates, it absorbs energy. When water condenses, that energy is released. Storm systems derive enormous power from this process. Hurricanes, for example, are fueled by warm ocean water evaporating into the atmosphere. The condensation of that vapor releases latent heat, strengthening the storm. So once again, a microscopic property, hydrogen bonding, influences planetary scale energy flows. The strange case of heavy water. There is one more fascinating twist in water's story. Not all water molecules are identical. Most water molecules contain ordinary hydrogen atoms, each with one proton in its nucleus. But hydrogen has heavier isotopes. One of them is deuterium, which contains one proton and one neutron. When a water molecule contains deuterium instead of regular hydrogen, it becomes heavy water, written chemically as D2O. Heavy water behaves almost like ordinary water, but not exactly. It freezes at a slightly higher temperature. It boils at a slightly higher temperature. Its density is greater. Even biological systems notice the difference. In large quantities, heavy water can interfere with cellular processes because biochemical reactions depend on precise molecular motion. Nuclear reactors sometimes use heavy water as a moderator to slow neutrons during fission reactions. So the smallest changes at the atomic level, adding one neutron to hydrogen, alter the behavior of an entire liquid. Once again, the story of water reminds us that the physical world is deeply interconnected. The hidden complexity of a simple molecule. By now, you might be noticing a pattern. Every time we try to treat water as a simple substance, we discover another layer of complexity. Water climbs surfaces. Water expands when freezing. Water stabilizes climate. Water dissolves countless materials. Water stores heat. Water forms hydrogen bond networks that rearrange trillions of times per second. It is both simple and astonishingly complicated. And yet, all of these behaviors arise from just 3 atoms, 2 hydrogens and 1 oxygen. That simplicity is deceptive, because when billions of such molecules interact, the resulting system becomes extraordinarily rich. And that richness is exactly what makes the natural world interesting. Water in space, the cosmic traveler. So far, we have talked about water as if it belongs only to Earth. Rivers, oceans, rain, clouds. But water is not just an earthly substance. Water exists throughout the universe. Astronomers have detected water molecules in interstellar clouds, in comets, on moons, and even in distant planetary systems. In fact, water may be one of the most common molecules in the cosmos. That idea might seem surprising at first, but chemically it makes sense. Hydrogen is the most abundant element in the universe. Oxygen is one of the most abundant, heavier elements produced inside stars. When hydrogen and oxygen encounter each other in the right conditions, water can form. Interstellar dust grains often act as tiny surfaces where these reactions occur. Hydrogen atoms stick to the dust. Oxygen atoms arrive, molecules assemble. Eventually, water ice forms on the surfaces of these microscopic grains. Over millions of years, these grains accumulate into larger objects, comets, and icy bodies. When a young planetary system forms, many of these icy objects collide with emerging planets. That is likely how much of Earth's water arrived here. In other words, the water in your body may have been created billions of years ago in a distant molecular cloud long before the Earth existed. Water is not just part of our planet, it is part of cosmic history. Water on other worlds. We now know that water exists across the solar system. Mars contains vast quantities of frozen water beneath its surface. Europa, one of Jupiter's moons, hides an enormous ocean beneath its icy crust. Enceladus, a moon of Saturn, sprays water vapor into space through massive geysers. Even distant dwarf planets show signs of water ice. These discoveries excite scientists for a simple reason. Where there is liquid water, there may be life. Water provides the chemical environment necessary for complex molecules to interact. Because of its solvent properties, its temperature stability, and its molecular flexibility, water allows chemistry to become biology. So when astronomers search for habitable worlds beyond Earth, they often begin by asking a simple question. Is there water? Exotic forms of ice. Up to now, we have talked about ice as if it were a single substance, but ice actually comes in many forms. The ice in your freezer is called ice-ich, a hexagonal crystal structure. But under different pressures and temperatures, water molecules can arrange themselves into many other crystalline patterns. Scientists have discovered more than 18 different forms of ice. Some are denser than liquid water. Some form only under extremely high pressure. Inside the deep interiors of giant planets like Neptune and Uranus, water may exist in a strange state known as superionic ice. In this exotic phase, oxygen atoms remain locked in a crystal lattice, while hydrogen ions move freely through the structure like a fluid. It is neither a normal solid nor a normal liquid. It behaves like both at once. Laboratory experiments suggest that superionic water may conduct electricity efficiently and could influence the magnetic fields of icy planets. This means that even something as familiar as ice has forms we never encounter in everyday life. The deeper we explore physics, the more variations we discover. What appears ordinary at human scale becomes extraordinary under extreme conditions. The final disturbing answer. Now we return to the question that began this journey. Why does water seem to break the rules of physics? The uncomfortable answer is this: it doesn't. The rules were never wrong. Our mental shortcuts were: human intuition evolved for survival in a world of rocks, trees, and animals. We did not evolve to understand hydrogen bonds, molecular networks, or quantum mechanics. So when a substance behaves differently from our expectations, we assume something mysterious is happening. But the deeper explanation is often simpler. Nature obeys consistent laws. Those laws operate at the level of electrons and atoms. When enormous numbers of particles interact under those laws, surprising patterns emerge. Water's strange behaviors are examples of emergent phenomena. From simple interactions come complex results. A tiny electric imbalance between oxygen and hydrogen leads to hydrogen bonding. Hydrogen bonding produces molecular networks. Those networks generate density anomalies, surface tension, heat storage, and solvent power. Those properties shape climates, ecosystems, and biological systems. And suddenly the ordinary glass of water on your table becomes one of the most remarkable substances in the universe. Physicist Richard Feynman often emphasized that science is not about memorizing facts. It is about understanding relationships. If you trace water's strange behaviors back far enough, they all connect. Electrons determine molecular structure. Molecular structure determines bonding. Bonding determines collective behavior. Collective behavior determines the physical world we experience. So the real lesson of water is not that it breaks physics. The lesson is that physics is deeper than our first explanations. And that depth is where the beauty lies. The next time you hold a glass of water, remember what it truly represents. Those molecules may have formed billions of years ago in a distant stellar cloud. They traveled through space, inside comets. They helped shape oceans, storms, and rivers. They participated in the chemistry that produced life. They now circulate through your body, carrying heat, nutrients, and information through cells. 3 atoms, 1 molecule, and a universe of physics hidden inside it. That is not ordinary. That is extraordinary.